All right, so now we're going to spend some time going into three-dimensional rigid body motion. Rigid body kinetics. And 3D rigid body kinetics, one of the things that's sort of surprising about it, like when you go from 2D to 3D, most of the time nothing changes that much. You add a new component and things stay the same. But every once in a while something pops up that throws a wrench into things. And with 3D rigid body kinetics, the main thing that throws a wrench into the works is the contribution of the moment of inertia. That seems weird because when you go from 2D to 3D in translational kinetics, mass doesn't change. But the mass moment of inertia, its effect on things changes a lot when you go to 3D. And here's the reason. So in 3D kinetics, mass moment of inertia gets complicated. And that affects all your calculations. So let me just first give a sort of a simple description of why that is. Okay, so why does it get complicated? So first think of 2D. So at instant 1 in 2D, say here's your coordinate system. And your body starts out in this configuration. Let me do these in a different color. Okay, so here's the coordinate system. There's the body sitting in the coordinate system at instant 1. And now the body moves before instant 2. So here's the coordinate system. And here's the body. Well, at instant 1, the mass moment of inertia so if we're rotating about the center, is 1/12 ml squared. And now it's rotated some amount. How do we calculate the mass moment of inertia at instant 2? Well, I made that sound like a trick question. It's exactly the same because the relationship between the body and the axis that it's rotating around hasn't changed. Okay, so the mass moment of inertia is still just 1/12 mass length squared. There's no change. So this is easy to work with. Okay. Now in 3D, here's instant 1. So there's the coordinate system. And here's the body. And you get that the x mass moment of inertia about the center is equal to 1/12 ml squared. The y moment of inertia about the center is equal to 0 because we're assuming that's a slender rod. And the z moment of inertia is equal to 1/12 ml squared. Okay, so, and you make a mass moment of inertia matrix out of this. It's messier, but it's not horrible. But now let's think about what happens at some general instant 2. Now this body can go anywhere, so our new orientation is this, say. Okay, the body's rotated not just about one of those axes, but it has a general rotation that involves all of them. So now what's the moment of inertia matrix? And it gets really complicated. Okay, so the mass moment of inertia changes in time. And that means that in 2D, we expressed the rotational version of Newton's second law as the moment is equal to the mass moment of inertia times the angular acceleration. The real law, the real rotational Newton's second law, sort of the base one, is that the net moment is equal to the time derivative of the angular velocity. So an h is equal to mass moment of inertia times an angular velocity. Sorry, I said angular velocity. This should be angular momentum. Okay, and so in 2D, since there's no change in time of the mass moment of inertia, the time derivative of the angular momentum is equal to I alpha. In 3D, since the mass moment of inertia is changing in time, these aren't equal anymore, because you'd have to use the product rule for the time derivative of the mass moment of inertia. Okay, so that's sort of how the fact that the mass moment of inertia is changing in time kind of reaches in and affects everything that we do in 3D in a way that it didn't in 2D. So we'll have to do the following things. First, we'll have to use this form of the rotational Newton's second law. For A either fixed or at the center of mass. And then second, this is the most painful part of it, is we're going to have to use rotating coordinate systems so that we don't have to deal with the moment of inertia changing in time. So where this mass moment of inertia matrix doesn't change in time. So we're going to have to spend a little bit of time talking about the mass moment of inertia, how to represent it in different coordinate systems, and that kind of thing. Anyone have any questions so far? So this is just supposed to be kind of an introduction to where we're going with 3D kinetics and why it's going to look so different from 2D kinetics. So before we get into that, I need to go through one new mathematical preliminary that we've talked about in my statics class a little bit, and we've talked about in my deform class, but we haven't in this one yet. And that's rotation matrices. So this is the rotation matrix. I'm going to call it Q. And here's the idea. Say that you have a vector V expressed in a coordinate system A, and I'm going to use this notation for a vector expressed in a certain coordinate system. It's like I'm going to use the relative sign. So you have a vector V relative to A expressed in coordinate system A, and you want to express it in a new coordinate system. In a new coordinate system B. So then that vector would be V relative to B. The way you do that is V relative to B is equal to a matrix times V relative to A. So it's an easy calculation to do that transformation. Where Q is a 3 by 3 matrix whose columns are the coordinate axes of A, expressed in the B coordinate system, in coordinate system B. most of the time, so this is a general definition of that rotation matrix. Most of the time, you're not going to calculate it that way. You're going to calculate it as rotations about specific coordinate axes. So this is a more common way to do it. Let me word this differently. If aligning coordinate system A to coordinate system B requires rotating A and then in the following ways. So there's 3 axes you could rotate A around to make it line up with B. The first one is an angle theta about the x-axis. Then your Q matrix is 1, 0, 0. And then down the first column, 0, 0. And then filling in the last 4 values, the cosine of theta, sine of theta, negative sine of theta, cosine of theta. Okay, so if that says if to go from your original coordinate system A to your new coordinate system B, the way you do that is rotate your coordinate system A theta degrees about x, then this is your matrix Q. Second, if to get from A to B you rotate A theta degrees about the y-axis, then Q is equal to, it looks sort of similar in form. Nope, that's not a 0. That should be cosine of theta, 0, negative sine of theta, 0, 1, 0, positive sine of theta, 0, cosine of theta. And notice the similarity of form. You still have the 1 in the diagonal for that axis, zeros in that corresponding row and corresponding column, and then cosines and sines in the off positions. And then third, if you're rotating theta about the z-axis, then Q is equal to cosine theta, sine theta. So I'm just going to fill in these first 4 values first. Negative sine theta, cosine theta. And then in the third column, 0, 0, 1, and then zeros in the last 2 spots. So the thing to notice about these is that the form is similar, but the signs are switched for the rotation about y. Okay, so for x, you had, for the rotation about the x-axis, you had cosine, positive sine, negative sine, positive cosine. For the z-axis, same thing. Cosine, positive sine, negative sine, cosine. For y, the signs of the signs, the plus minus signs of the trig function signs are switched. So you have cosine negative sign, sine, positive sign, cosine. Okay. So let me do two examples. One is just a vector, simple vector example, and then let me show how this could come up in dynamics with vectors. So say that you have a vector. Here's your coordinate system A. And the vector in this coordinate system has a length of 10, and this angle is 30 degrees. And say that you want to express that vector in this new coordinate system B that looks like this. So there's the horizontal. There's the coordinate system B, where this angle is 60 degrees. That means this angle is 30 degrees. Your vector stays the same. Your vector stays in place. It's just the coordinate system changing. And we want to use what we know in coordinate system A to come up with the components of that vector in coordinate system B. So vector V relative to A, to calculate that, this is just you calculate vector components like this all the time. That would just be positive 8.66, negative 5, 0. I'm not going to write this down, but to express it in the new B coordinate system, what are the components going to be? 0, 0, negative 10, 0. So when we do this coordinate system transformation, that's what we know we should get. So to do this, how do we have to rotate coordinate system A to make it line up with coordinate system B? Yep, and about what axis? So positive 60 degrees about the z-axis. So Q is equal to cosine of 60, sine of 60, 0, negative sine of 60, cosine of 60, 0, 0, 0, 1. And if you multiply those out, you get 0.866. No, you don't. You get positive 0.5, positive 0.866, 0, negative 0.866, positive 0.5, 0, 0, 0, 1. So now V expressed in coordinate system B needs to be Q times V relative to A. So that's the matrix 0.5, 0.866, 0, negative 0.866, 0.5, 0, 0, 0, 1, multiplied by our vector V in coordinate system A. That was 8.66, negative 5, 0. And if you multiply these out, your calculator will do that. It gives you 0, negative 10, 0. So that's the vector v expressed in the b coordinate system. Any questions about that example? So these rotation matrices are a way to take a vector expressed in one coordinate system and express it in a new coordinate system. Here's something you need to watch out for. Sometimes in textbooks, it's, I don't know, maybe 50-50, maybe more like 60-40 does it the way I'm showing you, and a little bit smaller numbers show it this other way. And you have to be careful because they look similar, but they give you opposite results. Sometimes in textbooks, give rotation matrices that rotate the vector while keeping the coordinate system constant. Those matrices look very similar, but it has the effect of being the opposite rotation. So you always have to be clear about whether you're trying to rotate the vector or rotating the coordinate system. In all my classes, I only talk about rotating the coordinate system, and if I ever want to rotate a vector, I just do it as rotating the coordinate system, so I never deal with the two different types. But you might come across this, and when you do, you'll see that the difference is everything looks exactly the same except the negative is here and the positive is here. The positive's here and the negative's there, you know. It's subtle enough that it's very confusing. But so if you ever see something and you're confused, like, wait, the signs look backwards or whatever, this is what you're seeing, is that you're talking about the difference between rotating a vector in a set coordinate system and rotating a coordinate system with a set vector.
So
yep.
If you're rotating a vector, wouldn't you rotate that negative 60 to get to the 1?
Yes.
So that's kind of where that negative comes from?
Right. Yeah, or you could think of it as like rotating, where's this example? Rotating the vector, rotating this vector negative 60 is the equivalent of rotating the coordinate system positive 60. So they're equal and opposite things. That's just something to be aware of. Everything I talk about is going to be rotating coordinate systems. Okay, so now let's do a dynamics example. And this has to do with rotating coordinate systems, you know, coordinate systems that are changing orientation in time. So let's think about cylindrical coordinates. And remember, with cylindrical coordinates, if you think of this as x and this as y, the cylindrical coordinates work like this. The particle is moving around, and the axes are oriented so that the r-axis always points toward the particle, and the theta axis always is perpendicular to that. And this distance is r. Okay, so let's just quickly derive the equation for the velocity vector in cylindrical coordinates. We have to use the fact that, so what's deceptively tricky about this is that as that particle moves around, that coordinate system is moving around, the axes are moving. So we have to use the stuff we've been doing recently about rotating coordinate systems in order to calculate the velocity vector. All right, so the position vector in cylindrical coordinates is equal to RER plus 0 E theta plus 0 E Z. And in the simple matrix form, I'm going to write this R0, 0, where this one corresponds to E theta, and this one corresponds to EZ. If this wasn't a rotating coordinate system, to take the time derivative of the position vector to get the velocity vector, you just take the time derivatives of the components. But in a rotating coordinate system, we have to do this as the time derivatives of the components. Actually, those should be, so this is PR, this is P theta, this is PZ. So we'll take the time derivatives of the components and then add that to the angular velocity of the coordinate system crossed with the position vector. The angular velocity of the coordinate system is 0, 0, theta dot. And so we can write the velocity vector as, so what's the vector of time derivatives of the components? That's right, r dot 0, 0. That position vector was r0, 0, so you just take the time derivatives of the components. And then plus capital omega 0, 0, theta dot crossed with the position vector. And you get r dot 0, 0 plus 0 positive r theta dot 0. And so in cylindrical coordinates, the velocity vector of the particle is r dot r theta dot 0. Okay, so now let's do an example where, say, the particle's motion is defined by r equal to 2t and theta equal to 5t. We want to first calculate the velocity vector in the xy coordinate system. Then we want to calculate the velocity vector in the, I guess that's xyz, in the r theta z coordinate system, the polar coordinate system. And then we want to compare those two. We need to be able to get the same answer for those two. Okay, so to get the velocity vector in the XYZ coordinate system, you need to recognize that the position vector is just equal to r cosine theta, r sine theta, 0. Anyone confused about that? Yeah. So if we're going on this green coordinate system, and this is the particle P, to come up with XY components for that point, it's just trigonometry. This length is r, and so the x component is just going to be r times cosine of theta. The y component is just going to be r times sine of theta. And so that gives you the position vector. So to take the velocity, since the XYZ coordinate system isn't rotating, we just take the time derivatives of the components. So the velocity vector is r dot cosine theta plus r theta dot, this should be minus sine theta. I'm just taking the derivative of that. Did I do that right? And then for the second one, I'm just using the product rule here. R dot times sine theta plus r times theta dot times cosine theta, and then 0. And so now you can plug in the values for r and theta dot, r and theta. Notice that if this is r and this is theta, r dot is equal to 2, theta dot is equal to 5. So V is equal to 2 times the cosine of 5t minus 2t times 5 times sine of 5t. And then the y component, r dot is 2, then times sine of theta plus r is 2t, theta dot is 5, cosine of 5t, and then 0. Okay, so that's, it gets a little messy. We can simplify that to 2 times cosine of 25 minus 50 sine of 25. Oh, I see. You know what? Okay. Here's, so what we want to do is when we do our comparison, we want to do this at a specific time. So I chose t equals 5 seconds. Okay, so let's put that aside for now. So what we have is we have the velocity as a function of time. The velocity of that particle is a function of time. Okay? We're going to get the velocity as a function of time in cylindrical coordinates. Then we're going to plug time equals 5 seconds into both of those two vectors, and they need to match up. Okay. So for now, I'll just simplify this as 2 cosine of 5t minus 10t times sine of 5t. And then 2 times sine of 5t plus 10t cosine of 5t, and then 0. Okay, so now so this is it in the XYZ coordinate system. Now let's do it in the polar coordinate system. We came up with the function, so V equal to R theta dot 0. So that's equal to 2. And then R theta dot is 10t, and then 0. Okay, so here's our function in XYZ coordinates. Here's our function in polar coordinates, cylindrical coordinates. Now we want to compare at time equals 5 seconds. In XYZ coordinates, plug in t equals 5 seconds, and we get a velocity vector at 5 seconds of 8.6, 49.3, 0. And plug in time equals 5 seconds to the polar coordinates, the cylindrical coordinates. And you get a velocity vector at 5 seconds that's equal to 2, 50, 0. Okay, so if we did this right, they have to match. So why they don't match? So what's the problem? That's right. The problem is that right now, so we've calculated correct vectors, velocity vectors in these two coordinate systems. The problem is that right now, at this instant, time equals 5 seconds, the cylindrical coordinate system and the XYZ coordinate system aren't aligned. Okay? And so they don't match because the cylindrical coordinate system is rotated theta to, well, an angle of theta about the z-axis from the XYZ coordinate system. So what needs to be the case is if Q is equal to cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. for theta equal to 5 times 5, or 25 radians. This is in radians because we had to use the chain rule. Then the velocity in the cylindrical coordinate system has to be equal to q times the velocity in the x, y, z coordinate system. So q is equal to 0.991. This is just plugging in 25 radians in for theta. So q is equal to 0.991, negative 0.132, 0, then positive 0.132, positive 0.991, 0, 0, 0, 1. And the velocity relative to the cylindrical coordinate system is this matrix. Times the velocity vector in the xyz coordinate system, which was 8.60, 49.30, 0. And if you do that multiplication, you get 250, 0. Yay! Okay. Any questions about that calculation right now? If I would say I wanted to do this example because we've done a couple problems with cylindrical coordinates already, and if you're sort of hazy on how this works, understanding how this works, I think, will be a really important step to making sense out of rotating coordinate systems and cylindrical coordinates and what you're looking at. So one thing I want to point out, I think for everybody, when you first see this stuff, there's a hazy kind of confusion between rotation matrices, changing the orientation of the coordinate system, and dealing with the fact that the coordinate system is rotating in time. So the key thing to understand with this is that the rotation matrix Q deals with axis orientation at an instant. It doesn't deal with, remember, the main issue, the reason that we had to go into that whole approach for rotating coordinate systems is because it doesn't deal with I dot, J dot, and K dot. Those are the culprits that made us go into this whole section on rotating coordinate systems. The Q matrix doesn't deal with that. It only changes one orientation of coordinate system to another orientation of coordinate system. Any questions right now? Yep.
What would it look like if it were rotating more than one?
You can do it somewhat with, if it's rotating about more than one axis, most of the time, in my experience using these, I have used the definition, wherever that is. You probably just have to use the fact that your Q matrix has columns that are equal to the coordinate system axes of A expressed in the B coordinate system, rather than using this rotation about X or rotation about Y or rotation about Z. In some cases, you can come up with the position you want by first rotating about X, then rotating about your new Y, then rotating about your new Z. But it's sort of cumbersome, you know, because those axes after each rotation, they have a new orientation. You know what I mean? But a lot of times, I actually, yes, I have done work where I had to do stuff with this, and those coordinate system, those relative coordinate system axis orientations came out pretty naturally in the data that you were using. So it's actually, that definition, even though it looks sort of confusing, it's useful, you know. All right, so we'll keep going with this next time. Yes.